Welcome to our Chapter 6 lecture on energy and enzymes AP biology. This will be our first lecture in a series talking about the energetics or what powers cells. So we're going to start by taking you back to your physics classes and talking about the first law of thermodynamics. And what that says is that matter and energy cannot be created, nor can it be destroyed. So what you start with is what you're going to end up with, or energy in will be equal to the energy out. It is important to note, though, that both energy and matter can be transformed into different states. So what we need to remember when we're looking at things throughout this unit from the first law of thermodynamics is that when we look at chemical reactions, for example, photosynthesis, or we look at cellular respiration, what we start with, we have to finish with. We can't delete things or magically pull things out of nowhere. However many carbons we start with, we're going to have to finish with that many carbons. It can be rearranged. It can be in different chemical arrangements, but we always need to start and end with the same. Same thing with energy. If we start with this much energy, we have to end with this much energy. It may not be stored in bonds anymore. It may be released to do work or lost as heat, but that same amount of energy needs to be accounted for. So we've got to be good about keeping the books. So there's going to be two types of systems when we're talking about matter and energy flowing: open systems and closed systems. A closed system means there's nothing new coming in and nothing leaving. So eventually, if you have a closed system, you will eventually reach an equilibrium where there's no more movement, no more transfer of energy, and you end up with death. In an open system, there's constantly an influx of new materials, new matter, new energy coming in, and there's also going to be waste product leaving. So this means if stuff's coming in and stuff's coming out, you can continually keep fighting off that equilibrium. You can keep trying to wage a war against that death from the closed system. So is a living organism like this happy fat little frog here an open or a closed system? Well, living things are always going to be open systems. And you need to remember that because matter and energy will move into a living system, so things like food intake, things like bringing in oxygen, then we're going to transform that into matter and energy that we can use. So converting the sugars we eat into the energy we will use in the form of ATP that we'll use to power everything in our bodies, and then releasing waste products. So stuff's coming in, stuff's coming out. We're giving off heat all the time. So living systems are going to be open. There's stuff coming in, stuff going out. So anytime we talk about the ability to do work, it's going to be called free energy. And work is anything that requires atoms to be moved around through cellular actions. So basically everything you do is going to be small chemical reactions powering you. And you may remember from physics that there's kinetic energy, energy from movement, or potential energy. That's energy as a result of your position, stresses, or charges, or other factors. So, for example, something like sugar molecule is going to have a lot of potential energy because of all those bonds storing all that energy. And then when it gets broken down into its more component parts, that's going to be more kinetic energy. You now have the ability to perform actions. And it'll have less potential energy because all those bonds have been broken. And we'll be getting into a lot more details of this. But what you need to know right now for energy is just we're not losing energy, or we're not just wasting energy, but it's just getting transformed to a different type of energy. So we're going to use this equation called the Gibbs free energy equation. And it's going to tell us when we're looking at any type of reaction, whether energy is being put into the system or energy is being released from that reaction. So anytime you see a triangle, that means delta, and delta is change. So we have the change in G, or free energy. That G is from Gibbs, who was the man who created this equation. And that equals a change in H, which is enthalpy, and enthalpy means heat energy, minus the temperature in Kelvin. Again, we are in Kelvin, so that's degrees Celsius plus 273, times the change in S, or entropy. So some terms you're going to want to be familiar with. If our free energy is negative, that means we are exergonic. If our free energy is positive, that means we're endergonic. So exergonic means that we are after the reaction takes place, we are at a lower energy level, which means we've released energy. Exergonic reactions are going to be reactions where you are releasing energy so you can do work. Endergonic means you have more energy now than you did at the beginning. So what that means is we put energy in. We're putting energy in a reaction where we're looking to store energy for later. So anytime we end up with a negative free energy, you can say it's going to be an exergonic. If it's positive, endergonic. How I remember the difference between those two things is exer kind of sounds like exit. So exitgonic means energy is leaving. Ender sounds like enter. Energy is entering into the chemicals. Enthalpy, same thing. If it's negative heat energy, that's exothermic. So heat is leaving, we're releasing heat. Positive endothermic, heat is entering into whatever our chemical compound is. And then we'll be talking a little bit more about entropy on a later slide. But what you need to know for right now is that is the disorder or chaos in the universe. So we're perpetually fighting entropy. We're perpetually fighting entropy, which means we're looking to fight us reaching that balance. If you remember that image of the closed system, entropy is pushing everything to that equilibrium, so everything is flat and evenly spaced out. And so we're seeing how much is fighting off that chaos. So as I said, exergonic reactions are releasing energy. And so you can see our free energy at the start in our reactants or our ingredients for a reaction is much higher than at the end, or the products, what we end with. Matter is being converted from high energy arrangements to lower energy arrangements. And so that means energy is leaving our system. Once you start one of these reactions, it's going to happen spontaneously. That means you can't put the genie back in the bottle, so to speak. Change in free energy is going to be negative. We're releasing that energy. Like most things, we want to fall down, kind of like when we were talking about water potential. It wants to go to the more negative area, so that's why it's going to happen spontaneously. That energy is looking to get released. It's easier to release energy than it is to store it. And so the opposite is going to be those endergonic reactions. Our reactants' free energy is much lower than our products. We're putting energy in. This cannot happen spontaneously. As you can imagine, it's much harder to cram things into a tight container than it is to release them. To put energy into those higher energy arrangements is not something that just happens like that. And so the important thing to remember here is biological systems will use those exergonic reactions, or releasing energy, to provide necessary free energy for endergonic reactions. So we'll release energy to use to put it somewhere else. So we'll power our endergonic reactions using exergonic reactions. Release some energy, use that to harness some energy. And so when I was mentioning spontaneous and non-spontaneous reactions here, you can see that kind of like a roller coaster, it's much easier to drop than it is to hike up that whole hill. So you need a little bit of energy always to get a reaction kick-started. Any input of energy required to start a reaction is called that activation energy. And you can see number one here is the activation energy. And on those endergonic reactions, it's a huge investment. And in fact, you have to put in even more energy than you end up with in your products. You'll lose off some there. And so that's why it's not spontaneous. It's not going to happen naturally. Versus an exergonic reaction, you put in that little bit of activation energy and you get that big release. So we're going to talk about two other words you should know with exergonic, endergonic, and these reactions is anabolism and catabolism. So anabolism is going to be building, and catabolism is going to be breaking down. So anabolism is building something bigger. Catabolism is taking something big and breaking it down into smaller components. So which of these reactions do you think would be exergonic? Yeah, probably going to be where we're going to have an catabolic reaction. So we're breaking apart those bonds, releasing that energy. Those catabolic reactions are typically going to be exergonic. On the flip side, anabolism, where we take small things and put them together, we're storing energy in those bonds by building that bigger molecule. Those are going to be those endergonic reactions. So your metabolism is basically the sum of all these reactions that are taking place throughout your body. Energy from catabolic reactions or breaking down, like cellular respiration, which we'll talk about next chapter, is going to power making ATP from ADP and a phosphate group. ATP is our cellular currency for energy. And so we'll use these catabolic reactions, breaking stuff down like sugar to get energy. We'll use that free energy to build ATP, which we can use to power other reactions in our body. And like I just mentioned, when we're talking about the cellular level, sugar provides us with our energy, and we use sugar, but we have to break sugar down. Sugar is a really great long-term storage molecule, but it's not good for instantaneous usage. That's what we use ATP for. But ATP isn't good for long-term storage. And so we have to continually make ATP in order to break it down to power our bodies. In fact, tens of millions of ATP molecules are made and used per second per cell in your body. In fact, you consume your body weight in ATP every single day, which always blows my mind. So if we look at that, the average human uses and regenerates about 75 kilograms of ATP a day. If we look at that from a chemistry perspective, since 1 mole is 6.02 times 10 to the 23rd, and we multiply that out with our ATP, that is a lot, 9.03 times 10 to the 25th ATP molecules per day, which is an astronomical amount. So you're using a lot of ATP, which is why we have to store energy more long-term in forms of sugars and lipids. So, second law of thermodynamics is going to be talking about entropy. So like I said, that's the measure of disorder or chaos within a system. And the second law of thermodynamics states that you can never decrease the amount of entropy in a system, but you can fight to prevent it from normalizing everything where you just freeze and die. Energy and the matter that accompanies it can be used to decrease in open systems entropy. And in order to maintain internal order, organisms must process ordered form of matter into less ordered forms. So what does that mean? Well, in order to maintain everything in your body, so like we were just talking about membranes, in order to keep things on one side of a membrane or the other, we're going to need energy. Diffusion, which is a major force of entropy, wants everything to be equal, everything to spread out. Nature loves to continue to spread out, make everything equal, make sure there's no movement or no heat, and then so we're perpetually fighting that. That would kill us as a creature if everything were just equally distributed. We have membranes because we try and organize and compartmentalize things so that our bodies can continue to function. And so in order to make this all happen, we need energy. So a good way to think about entropy, how you can't go back, is an egg is very ordered. You've got your yolk and your albumin protein inside of a shell, nicely contained. And when you break that egg, that comes spilling out. There's pieces everywhere. And it's becoming more disorganized, more spread out, less organized. And you can't go back. You can't put the egg yolk back inside the shattered shell. Same thing with like solid, liquid, and gas. A solid is going to have less entropy because it's very organized, very tightly packed. But a gas spreads out, it diffuses, it's much more random in its structure and organization. And so there's going to be more entropy there, where it's spreading out, more random, less order. So what is a good example of entropy in action? Here I have really well organized beans. There's white beans on top and red beans down below. They're nice and organized, nice and a lot of structure there. We can see the clear layers. But over time, that starts to get interrupted. Life takes place, things exchange. Your molecules are interacting, they're randomly bouncing off one another. And as you continue to see those interactions take place, now we are much less organized. Things are no longer in the same pattern they were. And if I want to go backwards, I'm going to stir in the opposite direction. I'm not going to ever be able to return to that state. It's very hard for me to fight off that entropy. Unless I put in an excruciating amount of energy, pour them all over the table and resort them, I'm never going to get back to those nice clean layers. And that's, I think, just a good mental visualization of what we're talking about when we talk about entropy. So when we go back to this equation, exothermic reactions that increase entropy are always going to be spontaneous or exergonic, and those endothermic reactions that decrease entropy are always going to be non-spontaneous or endergonic. So if we're increasing the amount of entropy because nature is looking to increase entropy and spread things out, those will be spontaneous. Those just occur. Those are going to be exergonic. We're releasing energy from its shackles. Anytime we're decreasing entropy, we're fighting against entropy, those are going to be non-spontaneous. You have to put in a lot of energy in order to overcome that disorganization that happened with entropy. And that's going to be endergonic. We're putting energy in. So when we're talking about these chemical reactions that are taking place, we can decrease the amount of activation energy that is required to get them to happen. And we're going to do that using something called a catalyst. Any substance that's going to increase our rate of chemical reaction, make those chemical reactions speed up, happen more rapidly, is going to be called a catalyst. Catalysts not only lower the activation energy of a reaction, but they're reusable, which means that those catalysts can continue to work until all of our reactants have turned into products. And so here's a great just visual of a graph of how much energy is required to get from reactant to product. Instead of having to climb up that activation energy, that catalyst is going to make those reactions much more energetically favorable, which means we're taking away some activation energy by creating conditions that make for the reaction to happen more spontaneously, or the reaction to happen more easily. So how does that work? Well, let's take a look at one form of these called enzymes. Enzymes are proteins that act as catalysts by reacting with something called substrates. So the reactants of a chemical reaction are going to be called a substrate when it's interacting with an enzyme. Enzymes cause either the catabolism or anabolism, and remember, that's the breaking apart or building. And if you're looking for a way to remember those terms, how I always remember it is cats, if given enough time, are always going to break something. Cat sitting up on a shelf next to a vase is going to knock it off. It's going to break. Cats will break things down. You may have heard of anabolic steroids. People who take anabolic steroids are looking to get bulky. So anabolism is bulking up, getting bigger. Catabolism, that cat knocking something off a shelf, that's breaking it down. Anyway, enzymes are going to cause either the breaking or making of bonds by making those bonds more energetically favorable. So this is going to happen at something called the active site. So this place where you see the reactants coming in is going to be called the active site. And that's where the enzyme works on those reactants. And it's shape and charge specific. So not only does it have to fit the right shape, but the charges in the active site need to match up. Remember, proteins are made of amino acids, and amino acids have those side chains with different chemical properties. Well, if the chemical side chains match up with the chemicals in the substrate, it'll make a favorable reaction site for the products to be released. So there's two models with this. Originally, it was a lock and key model, where you can think of the substrate as a key, the enzyme as a lock. In order for that lock to be opened or the reaction to take place, that specific substrate has to fit perfectly into the enzyme and the reaction takes place. This is a really good analogy that you can use, but it's not an exact scientific principle. In reality, it's more like induced fit, where there's an open active site, and those chemical reactions cause that enzyme to fold or have a slight conformation change. Ooh, that word coming back, conformational change, the shape of a protein. So it's going to have a slight conformational change at the active site to mold around the substrate and cause that reaction to take place. Something that can help with enzyme activity, there's two things. One is called cofactors. These are accessory compounds. So vitamins and minerals, you may have heard like, oh, you got to eat your vitamins and minerals. Well, here's why. It's powering your enzymes. So vitamins or metal ions that are minerals may be required for the enzyme to properly function. So a manganese ion in topoisomerase allows for topoisomerase to grab onto DNA to do its unwinding behavior. And it's providing just the necessary chemical interactions for that to take place. Magnesium ion is present in rubisco, which is involved in photosynthesis. And so these ions are very important. They're going to be called cofactors. There's also something called a coenzyme. You're going to be hearing a lot about these things called NAD and FAD when we get into cellular respiration. And they are coenzymes, or little shuttles that carry things to an enzyme. So they're just little helpers that help basically carry certain things around for chemical reactions to take place. Enzymes can be regulated in a few different ways, and enzymes can be either stimulated, where they're turned on, or inhibited based on a couple factors. Most of the time when we're talking about enzymes, we're going to be talking about inhibition. So there's competitive inhibition, where something binds to the active site, and so our substrate can no longer bind to the active site. That makes sense. Competitive, it's competing for access to the active site. Non-competitive inhibition is where it bonds to something called an allosteric site, somewhere else on the protein, and that's going to cause a conformational change. So that's going to cause that enzyme active site to change shape, and because it's shape specific, when it has that alternate shape, then binding is no longer successful. So I mentioned that was called allosteric. If we break that word down to its root components, allo is a prefix for other. You may remember that when we talked about allopatric speciation, where they were separated, so physically separated. They were in an other location. And steric is going to be location on our enzyme, so allosteric, in other location. And so this is going to bind not to the active site, but it can close off the active site, so it no longer is able to grab onto enzymes. Or it can activate it, where it binds to that allosteric site and it stabilizes the enzyme into an active conformation. And so those active sites would normally be closed unless there's an activator. Otherwise, in an inhibitor, the inhibitor comes in and closes those active sites. And sometimes the products that an enzyme makes can act as an inhibitor. So this is going to be an example of negative feedback, where you start to make something, and as that product builds up, you don't want to get too much of it, and so that product will bind to the enzymes and actually turn them off. And so the enzyme that starts the pathway that turns the amino acid threonine into isoleucine, that acts as an allosteric inhibitor for that enzyme. So basically what it does is it's like shutting off the lights when you are done in a room. Once the job's finished, it's going to turn off the pathway. So here we can see that we have an enzyme, and it's going to bind to threonine, and that's going to cause these changes to eventually make isoleucine. And then isoleucine will bind, when there's enough of that, it's going to grab onto those same enzymes and cause an allosteric inhibition. It'll change that active site's shape, so it's no longer usable. And so now threonine can no longer bind to it. And because of that, all of these secondary reactions won't take place, and we're going to stop making isoleucine. Once all your isoleucine gets used up, though, there's going to be no isoleucine to block these enzymes. These enzymes will be open, and then threonine can go back in to make more isoleucine. Sometimes the binding is required, and for stabilizing other subunits. So remember when we talked about quaternary, proteins structure, where there's the multiple amino acid chains together. So those multiple subunits of a protein. Sometimes a protein is turned off, and this is going to be called cooperativity, where it isn't very effective at binding to the substrate. But if it is able to bind to that substrate, that's going to cause a conformational change, and it's going to activate all the other subunits to allow them to perform their function. And one of the reasons I said earlier that most of the time we're talking about allosteric inhibition is it's going to cause more dramatic effects than a competitive inhibitor. So when you look at this graph, here's normal enzyme function, that as you increase substrate, what's the rate of reaction? We reach this like maximum rate of reaction. A competitive inhibitor, something that binds to the active site, causes a little decrease in the rate of reaction, but it's more of a delay. It'll eventually still get to that maximum rate of reaction. But an allosteric inhibitor, which can really break down because it causes that actual conformational change in the protein, can actually cause a huge shift. So if you're really trying to shut down an enzyme, you want to do allosteric inhibition, not competitive inhibition. And an example of allosteric enzyme activity is caspase. What do you think caspase might do? Well, remember, ACE means protein, and the prefix is usually what it does. So like lactase causes, breaks down lactose, the sugar. So caspase, where have I heard caspa before? Caspa, the friendly ghost, casparase. Yeah, it's important in cell death, apoptosis and necrosis. So we have an allosteric inhibitor that is preventing that cell death. And that's really important because we don't want all our cells to die. So we want to make sure caspase is firmly locked down until we need it. So there's also environmental factors that can play a role in how enzyme activity works. Like all proteins, enzyme structure and therefore function, remember, it's the structure of a protein, the shape of a protein determines the function, will be affected by conditions of the enzyme's environment. So there's lots of different environmental conditions that can do this. Temperature, pH, heavy metals and salts. All three of those can really disrupt or break apart those connections and cause in a protein structure and can cause it to denature. And so if it denatures, it's going to lose its shape. If it doesn't have its shape, it can't do its job. It's not going to bind to an active site. Remember, if that active site gets unfolded, like with allosteric inhibition, it has that conformational change. It's denatured. It's not going to work anymore. Also, enzyme and substrate concentration, which makes sense. The more substrate you have, probably the faster it's going to go. So here we have rate of reaction versus temperature. And for normal human enzymes, we have 37 degrees Celsius, which is our core body temperature. And as we get too cold, you can see enzyme function goes down. You can see if you get too hot, you get a fever, enzyme function goes down. That's why having a fever is bad for you when you get sick, because if you get too hot, all your proteins will denature and you'll die. But thermophilic or heat-resistant bacteria that love like hot springs, their main best temperature is going to be 77 degrees Celsius. And when they get to regular human body temperature, they're dying off. And again, if they get too hot as well, they'll die off. This can also be seen in pH. So, for example, most enzymes, like your intestinal enzymes, have a pH around 8, a little above 7, where human pH is on the inside. But if you look at pepsin, which is in the stomach acid, that's going to have an optimal pH of 2. So you get too basic and it'll die off. You get too acidic and it dies off. Same thing here. We get too acidic, these proteins will denature. Get too basic, these proteins will denature. Finally, substrate concentration. If you keep adding more substrate, enzymes just randomly bump into substrate. So if you add more substrate, you're going to have higher enzyme activity. If it's easier to find, it's easier to cause that activity. However, eventually you have only so many enzymes. So if you keep dumping in more substrate, it's not going to do anything. Same thing with enzymes. If you have 50 pieces of substrate and 50 enzymes, it's going to go like that. If you have 50 pieces of substrate and 100 enzymes, well, only 50 enzymes can work. So it's not going to go any faster. So it is important to know you'll have kind of a saturation point where eventually you can only go as fast as you can go, and you can't break down any more than that. And compartmentalization, thinking back to when we talked about cells, because they're going to randomly bump into things, it's important to keep enzymes concentrated because of that saturation point. The more concentrated, the higher that saturation point. And so we're going to make sure in our cells that we store enzymes in specific organelles, in specific places, have them clustered together so we can increase the likelihood that it bumps into that substrate. So some key take-home things you want to make sure you learned. Gibbs free energy equation. be able to use it and understand what it means when it's positive or negative. Same thing, those exergonic versus endergonic reactions. Exergonic, negative Gibbs equation, releasing energy. Endergonic, positive, putting in energy. That goes right there with anabolic reactions where we're building, catabolic where we're breaking apart. You should be familiar with enzyme structure and function, both active site, substrate, but also those allosteric spots with those enzyme regulation and inhibition. How do we turn enzymes off? And then environmental factors that can influence that. Remember, going back to that conformation of proteins, you change the environment, you denature the protein, change the shape, doesn't work no more. So hopefully this was helpful. Have a great rest of your day, and feel free to ask me questions when they come up.